Well, hello, everyone. I'm very happy to be speaking to you again. My last time at JDD was in 2019, just before all of this started. So I'm really looking forward to the next time I can visit you there in Krakow. But for now, I can say that the travel is certainly shorter from my kitchen to my office than flying from Florida to Europe. Today, I'll be talking to you about the killer Cs. I was somewhat inspired by the murder hornets and killer bees that we've been dealing with here in the US this past year. But I was also thinking about other killer Cs, and particularly cholesterol in the world of human health. And so maybe that's the fourth killer C is cholesterol, but that's one that I can't do as much about. A little bit about myself. I've been a developer for a long time. I've been a software architect, enterprise architect. I've also spent some time in operations, and it was my time in operations that led me to write this book called Release It, to help developers build software that survives the real world rather than just passing QA. I'm happy to say that that's been received very well, and many of its techniques have become quite commonly used, which I think has improved our availability overall. I'm currently a leader of software engineering inside a company called Sabre. Many of my colleagues are there with you at JDD and in Krakow in general. Of course, because I am here with Sabre, I also have to say that these statements and views are my own, and I'm providing them as myself. They are not Sabre's strategy or views particularly. Now, what I'm going to talk about today is how these killer Cs can harm or help your application. And there will be times when this begins to sound like a commercial for some pills and medication. This is the point where I have to say that I am not a doctor. This is not medical advice. I'm not telling you how to deal with your cholesterol. But if I were, and if this were one of these medication ads, this is where I would tell you that side effects of this medication could include blurred vision, missed deadlines, dizziness, and a desire to rewrite your entire system. The cure for these conditions is not a pill, but design. And fundamentally, this is a talk about design and how to see forces at work inside your application that your design can either create and cause difficulty, or where your design can succeed well. Now, all of us are doing design all the time. We tend to divide roles inside software up into these sort of scoped tiers where we talk about developer, lead, architect, enterprise architect. The truth is that all of us are doing design, from naming a variable inside of a function to allocating behavior to modules, to even determining which projects and systems should exist and what they should do. The challenges in design are that we are simultaneously thinking about several dimensions. We're thinking about the components and modules. Whenever I say a component, I mean a thing at runtime. Modules are things at development time, so source modules and libraries. We're also thinking about the allocation of behavior. Just how do I make something work at all? And then we're thinking about how much information do I expose at those boundaries between components and modules. And we have nested boundaries all the time. And so this notion of boundaries and information exposure, we sometimes also talk about in terms of information hiding. And actually, one of the people who gave us the term information hiding, David Parnas, later said he should have called it decision hiding, which is an interesting interpretation, that you want to hide as many decisions as possible so that decisions in different modules are independent of each other. Now, these killer Cs, coupling, cohesion, and complexity, we had once believed some of these to be purely harmful and some to be purely helpful. But like cholesterol, we now know that the story is more nuanced, more complex, I guess I could say. And that some of these are unavoidable, and some of them can actually be beneficial in certain contexts and harmful in other contexts. So we will dig in and look at these in somewhat more detail. We'll begin with coupling. This is like the high density lipids of software. People have discussed coupling as a purely negative thing. It inhibits you from changing. Anytime something is, harder than expected or changes have a ripple effect, we blame coupling. Frankly, as we dissolve large systems into constellations of microservices flying in formation, coupling becomes ever more important. And we actually shift a lot from static coupling to dynamic coupling. In other words, moving from coupling evident in the source code to coupling evident at runtime. Now, coupling is a dirty word in our industry. We use it as a synonym for bad because it kind of keeps us from changing. But coupling in the real world or in other fields is not a dirty word. In fact, it enables and creates structure, and it creates structure in ways that are necessary. When we talk about coupling, the challenges that come from it is that we all know changes within a module are much easier than changes that have to span modules. And so it's this change across modules that we think of as the harmful form of coupling. But let's look at some other fields and how they address coupling. For instance, in mechanical engineering, coupling can create safety. So the device I show here is the Scharfenberg coupler. It holds train cars together in a way that cannot accidentally become uncoupled while the train is moving down the tracks. It requires a deliberate action, and the normal movement of the train will not result in uncoupling. I've used this example before. In fact, last time I was at JDD, I showed this example of Watt's linkage, which is a coupling used in mechanical engineering to turn rotary motion into linear motion. You'll notice this has 3 beams and 4 couplers that can pivot. We also have the Chebyshev linkage, which was developed later and is a better way of turning rotary motion into linear motion. And this one also uses 3 beams and 4 couplers. It's the same parts, but a different arrangement. And it's that arrangement of parts that creates the motion. If you didn't have the coupling here, you would just have a pile of parts laying on the ground. I am also something of a physics buff, I guess. It's a hobby, you might say. And in physics, we have this thing called the standard model. You've probably seen a diagram that shows the particles laid out in a manner similar to the periodic table of elements. This diagram shows how the particles couple to each other. And there are some interesting ones here. For example, the coupling between the photon and the electron, shown as one of the blue arcs on the left. Well, that creates the electromagnetic force, which is why we don't fall through our chairs to the center of the Earth. Coupling to the Higgs boson down at the bottom is what we believe now gives mass. And so without those 2 couplings, nothing would exist. So coupling is not inherently bad. It does determine the degrees of freedom that you can use to move a system or change a system. In other words, the kinds of replacements you can make, the kinds of adjustments you can make. Whenever you're redefining the relationship between a couple of components, the coupling between those components determines what you can move. So it enables some of those movements, but it inhibits others. And this is where it gets its bad reputation, is that inhibition. Coupling also connects effects from one place to another, and this is actually necessary. If our software was completely decoupled, nothing would call anything else, and it would be like a pile of parts on the ground. It wouldn't do anything. So in order for our software to do anything, some degree of coupling is necessary. We need to think about what kind of coupling to create and what kind of coupling to allow. and how we can make that coupling enable as many degrees of freedom as we want and inhibit as little as we want. In analyzing this, I came up with these 5 different kinds of coupling. These are modes, if you will, that display themselves in different contexts. So the operational coupling is something you see at runtime. When you have A calling B, if B is down, then A cannot run. So that's operational coupling. Development coupling is when you're making changes in source code and those code changes have to be coordinated. So you can think about something like renaming a class, renaming a method, adding fields to a structure, changing the signatures of a method. These are examples of development coupling. Semantic coupling is a little trickier because you can't always see it in the source code. Semantic coupling arises when you have different components that share ideas, but may have completely independent implementations. An example of semantic coupling is cardinality. So I may have 2 different systems that each have a cardinality about an order to payment. If one system assumes that one order has one payment, and another system assumes that one order can have multiple payments, then you have a semantic disconnect. And this means that when the semantics align, if I change the cardinality on one side of that shared concept, I have to change the cardinality everywhere. Functional coupling is sort of the reverse of that. This is where we don't necessarily have to share concepts, but we share some piece of implementation. That means we have to change both ends of a connection together. An example here would be switching from IBM MQ series connectivity to Kafka connectivity. Both participants need to change at the same time because otherwise they'll literally be speaking different languages and can't communicate. And then we have incidental coupling, which is things that are stuck together for no good reason. I had an example of this sometime back where an e-commerce system couldn't boot the application servers if the MQ brokers were not running. No good reason for that, but there it was. Now, I want to talk a little bit more about this development coupling and give you an example of what it can look like and one way of managing it well. And I'll stress that this is one kind of development coupling, not the entire universe of it. And here I'm talking particularly about nominative coupling, which is just an academic way of saying names. This is when names are being used across different modules and the exposure of those names and the dependency on those names create a need for common change. So I have here a brief code sample from Visual Studio Code, an editor that Microsoft has made available not only free, but open source. And this is an interface that particularly talks about positions in a file. This is in TypeScript, and there are 3 names here which are exposed: iPosition, line number, and column. Those names are available for anyone else in the source base to couple to, and indeed for extensions to couple to. And you can see that iPosition appears in quite a large number of places. Well, these are names. You'll notice that this is a pure interface. It doesn't really couple to anything else. And so it makes sort of a leaf node in the graph of coupling here. iPosition doesn't import any other names. It doesn't reference any other names. This kind of coupling exists all over the place. When you do an import, you are creating coupling to whatever it is you're importing by name. When you reference a class or a function, you're creating that same kind of nominative coupling. As an example of where this is used, we have the class range, one of these many 387 results, and you can see that range refers to eye position as a parameter type in these two functions. Now, this is an interesting sort of signpost in the war about types, because the presence of this type in these function signatures signals that that coupling exists, but the coupling would exist even if it weren't there. So in other words, if position were untyped, if we weren't in TypeScript, but we were in, say, pure JavaScript, this function contains position would still depend on the definition of position, but the coupling would be somewhat invisible, or you couldn't simply do a source code search to locate all the references to eye position and find where that is. And this is one of the reasons that people will get very adamant about types, depending on the projects they've been through and their sort of human path dependence, if you will. Some people will say types are mandatory for large-scale projects because they help expose that coupling information. Others will say types inhibit large-scale projects precisely because the more the type is referenced, the more places you may have to change when you change the interpretation of that type. I'm not at this point taking a position or claiming a side in this battle, but I will say grep is a very nice tool for locating things. Now, this kind of nominative coupling, when managed well, looks something like this. So we have a position implementation which couples to the position interface. At the same time, we have users of positions, range, iText model, and many others that also couple to the interface. And so this is kind of a classic structure. You've probably seen this pattern before. It should be pretty familiar. This is a very effective use of names, but the coupling still exists. Range can't work without some notion of positions. The text model can't work without some notion of positions. So the development coupling will be there. And in this case, coupling to the interface is cleaner and allows more flexible change. Things get tricky when you're dealing with modules that allow dependencies into them at runtime, libraries, any architecture with plugins. They all allow this kind of a construct where we have names that are not only exposed in the source code, but in this case, the names are exposed for dynamic coupling at runtime with these extensions being loaded. And so this is another place where we need to be very careful, and this is the kind of coupling that often gets us into trouble. Again, use of things like pure interfaces can help us deal with this. Use of things like add-only structures can help us with this as well. Add-only means you don't go back and remove fields. You use rules like Google protobufs, where it's always okay to extend with new fields, but existing fields must be left in place. So we'll turn our attention from coupling to cohesion. And this one is sort of like the low density lipids in the cholesterol model, if you will. We have sometimes thought that cohesion is a synonym for good. If we say something is cohesive, it means that, you know, we like it. If we go back and look at where the word comes from, as we often do, you'll notice a kind of duality here. On the one hand, we have this definition that says things stick together. It resists separation. But then we also have this idea that parts are logically connected so that aesthetic consistency results. I like both parts of this definition because I find them both to be true. There is a tension in the concept of cohesion, and it appears here in the definition. You'll also see it in some sort of snarky comments and old jokes in the programming world. We sometimes say that, you know, cohesion is what's inside a boundary that we like, and the same kind of connection is coupling when we see it across different modules. And so people have sometimes said, if we like how things are connected, we call it cohesion. If we don't like it, we call it coupling. There is some truth to this. I'll give you an example. Suppose I'm making a business change that says we want to add a birthday field to profiles so that we can, you know, give free stuff to the user, but we also get more information about them and can sell that information wherever. When we make this kind of a change, the concept of birthday is a pretty easily defined concept. It's a day of the year associated to a person. But in order to make that change, I have to make kind of the same change across many different layers. Now, same is, you know, a little bit loose here, because obviously in a form, I'm adding HTML field. In a view, I'm adding HTML output. In a controller, I'm probably doing some validation and parsing and so on. So obviously the code is different in each of these layers, but I have to do them all together in order to do the birthday change. And so what I'm seeing is that the cohesive notion of a birthday is kind of sticking things together across different layers of my architecture. So I've built an architecture that's oriented around the separation of concerns, views, controllers, models, persistence, tests, and so on. But this cohesive concept is connected across all of those layers. And so in a sense, the cohesion of that concept is working against the architectural separation. And sometimes that can result in a phenomenon that we would call architecture erosion, as that cohesive concept sort of wins and dominates. We have to do work to maintain the architecture layers, and that work is, you know, an ongoing energy requirement. This is a classic kind of layered architecture, whether you call it MVC, MVVC, M something C. These layers are pretty familiar, literally textbook architecture. There's another architectural pattern, doesn't have as many frameworks written around it, but I think this architectural pattern helps with keeping concepts cohesive, and it's called the ports and adapters architecture, or hexagonal architecture. This is one that I really favor. The premise is that the core depends only on other core elements, and these are all domain elements. They do not depend on persistence frameworks. They do not depend on HTML libraries or rendering libraries or any kind of communication protocol. You could run the core domain entirely by itself, and in fact you do in tests many times. Blending a little bit of domain-driven design concepts in with hexagonal architecture, you have this layer called anti-corruption, which is usually expressed in the form of commands and queries that would then operate against the core. The purpose of the anti-corruption layer is to keep the core intact and sane and valid, but it's also to expose a kind of API for manipulating the core that these adapters then use. And the adapters work by translating from the language of the domain, the commands and queries, to the language of the technology that you're using at the boundary. So an adapter from the core to databases at the core would talk about, you know, a command to create a user or a query to find a user by name. At the periphery, it talks about tables, schemas, columns, rows, queries, that sort of thing. And in between, you have layers that mediate between those two domains. Likewise, we can have another adapter for how our primary constituents interact with the core. We can even have multiple adapters for different populations, so that there is an adapter for operations that maybe accesses entirely different information. So this construct, each adapter can look like a little stack of layers. But by separating things this way, when I go to make a birthday addition to a user, I make a change inside the core and at the anti-corruption layer, but I do not create a new birthday table type or name or instance inside the database adapter. What I do instead is say that the user class inside the core becomes an instance of table at the periphery. So table becomes the type, and the user is just an instance of that type. So this is cohesion, how we can manage cohesion together with architecture at a large scale. Let's look at it at a small scale as well. So now we've zoomed way into a single class. Similar things apply to functional programming. But here I'm looking at methods and members in a class. And we can think about the members that a method accesses and draw it as a kind of dependency graph. Which methods access which members? And suppose we end up with a set of dependencies like this. Method 1 uses member 1 and 2. Method 2 uses member 1, 2, and 3, and so on. What you'll notice is that there's kind of a clear partitioning here where I see lots of connections within the bottom set and lots of connections within the top set, but not many between them. And so this is a place where maybe we would refer to this more as a lack of complexity or lack of cohesion rather than cohesion. If I saw this in a class, I would say this kind of wants to be two different classes. This wants to be split up into different things. And in fact, we used to have a metric in OO software quality metrics called LCOM, or the lack of cohesion of members. And LCOM would indicate when you had this kind of a situation, that you had this partitioning that, like all metrics, shouldn't be treated as a rule, but should be treated as a diagnostic to give you an idea where you need to look a little harder and where maybe the code is trying to tell you something that you haven't yet recognized in your design. So that's cohesion. Let's talk about complexity. Complexity, if I stick with the cholesterol model, complexity is the triglycerides, almost always harmful. We look at complexity as the result of dynamic processes that have created increased binding, removed our optionality, removed our ability to make changes. Gregor Hoppe tweeted not long ago that excessive complexity is nature's punishment for organizations that are unable to make decisions. I have to say that stung a little bit because it felt a little close to home. And what he means by this is that, when presented with option A and option B, many organizations have trouble definitively picking one and saying, we're going to do option A. They say, well, we'd rather do A, but maybe we need B. We might need to change it in the future. We don't want to have to go back and rework this software after we've written it. So why don't you make it so we could do either one? And the developer will go, well, okay. And they will, add in an interface to sort of abstract over the options. But then if you've got an interface with two concrete possibilities, you probably need a factory to build one or the other. And then if you've got a factory, you have to configure the factory. So you need some kind of configuration. And what could have been just one function or one class is now this constellation that requires coordinated change in several different places. So this is an example of development coupling that limits options. Even though it appears to enable options, it actually limits them, because if you decide that actually sometimes I want a little of option A and a little of option B, I can't really do that. I have to add maybe an option C, which is some of both. But then if somebody else wants a different mix of A and B, then I have to add an option D. And every time I do that, I need to go back and re-examine the interface and make sure that the factory can construct all of the things and that the configuration can deal with all of the things. And so by not making the choice between A and B, we've set up a construct where actually in the future, we can make more instances of this kind, but we've made it harder to do things which are not of this kind. And that's a little bit of a subtle distinction, but it's definitely a case where we can see how coupling both enables and inhibits different choices. And if you do this in many different places around your code base, you'll definitely lose the ability to change and maneuver. And we'll call it complexity as a dynamic process. There's an old phrase that says kludges cluster. Of course, no one can actually agree on how to spell kludges, so I'm taking a little bit of a position here that this is the proper spelling of kludges for an English speaker. But what it means is when I do something messy in one spot of my code, when I hack something in, when I create a little knot of complexity, we'll tend to create more knots of complexity over time. And so there's this feeling of entropy increasing in our code. This little model is a conceptual Markov model about making changes. Software that is easy to change has some probability of remaining easy to change every time somebody touches it, but it has some probability of transitioning from easy to hard and becoming hard to change. And likewise, every time you touch hard to change, there's a probability that it remains hard and a probability that it transitions to easy. I think we all understand that the probability of going from easy to change to hard to change is much higher than the probability of the reverse transition. That once something becomes hard to change, well, it's hard to change. And so it's hard to change it back to something easy to change. It requires work. And this is why, we talk about it as entropy, because it requires work to counteract that effect of entropy. Another dynamic process that creates complexity is boundary erosion. So imagine you start with a system that is nicely layered and nicely componentized. So, leaving the hexagons aside, we're looking at UI, model, persistence, and so on. But we're running these all in one large process. Maybe these are different DLLs or different jar files, but I'm bringing them together in one application. Sooner or later, there will be some kind of requirement that causes me to bridge between these components inside the domain layer. So from our users component, we need to access something about orders, or from orders to suppliers, or so on. And so we begin to get these horizontal connections. And this is erosion. And if you've ever lived in a 10-plus-year-old code base, you've probably seen this, that somehow each of these components has grown a kind of God class, which does everything inside that component and everyone else can access it. Once this sets in, you'll also begin to see other examples of boundary erosion, because the architecture itself becomes unclear and hard to see. So when the dependencies are very knotted, developers don't know what the boundaries were even meant to be. And so you get, vertical erosion, you get jumping layers across different components, and so on. So this is when people will start to refer to something as, the hairball or the big ball of mud, and start to agitate for rewrites. We can detect this early. It doesn't come automatically. You don't necessarily see boundary erosion happening just by looking at individual commits or pull requests, but you can see it if you apply some tools. So one of the tools that I particularly like is something called a design structure matrix. A well-architected system will have a very sparse design structure matrix. This is a matrix where components appear as both the rows and the columns of the matrix, and anywhere there's a dependency from component A to component B, you make an X in that intersection. Should be pretty sparse. That means that modules have few interdependencies. The less sparse it becomes, the more crowded it is, the more boundary erosion you've had. You'll certainly see the nominative coupling between modules increase as boundary erosion occurs. And you can apply a few diagnostics to your Git repository. If you look at commits and you identify commits and the files in them as belonging to different layers, if you find that you have a large number of commits that always include files across a common set of layers, you may have boundary erosion going on. All of these are time-oriented, and so you're looking at the change in boundaries and respect for boundaries over time. Speaking of time, when we have deployment processes, still on the subject of complexity, and in terms of ways that complexity increases, I pay a lot of attention to friction in deployment processes. I put a lot of effort into trying to reduce the friction because we have this sort of pathway where friction in the deployment process will cause people to avoid creating new deployable units. Because to create new deployable units means new things to track. Each new thing has to go through some kind of stage gate or approval processes to even be allowed to deploy. And so because that's difficult, people will tend to clump modules together in components. In other words, you may not intend to create new monoliths, but if it's hard to deploy things, people will tend to do fewer, larger deployments and group a bunch of things together inside of a single artifact. And that will also cause you to make infrequent releases, which will tend to be larger, which increases the risk during deployment. And risk during deployment leads to failed changes and defects. And this is where the doom loop really kicks in, because those failed changes and defects will tend to cause an increase in friction in deployment as scrutiny goes up. So the more failed changes you have, the more the organization will reflexively want more investigation, more review, more checkpoints, which further increases the friction, which creates more reluctance to build new deployables and weaker boundaries and more defects. Also larger, less frequent releases, and you can see how this is a kind of amplifying cycle. Well, if we're going to overcome complexity, there are some processes we can do. These are also time-oriented. One of the tricks you can do is actually first to draw a larger boundary, because complexity often comes in the form of excess interactions between components. You can first draw a larger boundary, re-architect within that, and then make smaller boundaries. So sort of melt it all together, separate it out, and then freeze the new crystals, if you will. I find that one of the best ways to reduce complexity is to remove special cases. So you'll hear me talk about simplification through generalization. Another great technique is to replace code with data. So if you have, a bunch of nested logic and decision trees and so on, maybe look at a table-based structure in your code, or maybe look at ways to replace specialized point-to-point interface calls with, custom code for each client API. Replace that with a generic caller that just operates on URLs and knows how to invoke any URL. Definitely, complexity creates a need for implicit knowledge. Making that implicit knowledge explicit will help first expose the complexity, and then will help people tackle the complexity. But when it's all held in people's heads, there's not a lot you can do. The anti-corruption layer from domain-driven design is a really good way of overcoming complexity, because it allows you to reduce the number of direct calls into the core of a system, and it helps you recreate a boundary. Sometimes the strangler pattern is the only way to go. You just put a wall around the excessively complex part of your system, and then strangle it with something newer and hopefully simpler. And one of the things that I often really advocate is disposable code. Code is not an asset, it's inventory. It's an ongoing cost. You have to maintain it, you have to store it, manage it, and so on. So the less code we have, the less places there are for complexity. And when we write disposable code, we can constantly renew and refresh that, so that we don't have to live with accretion of complexity over time. So those are the killer C's: cohesion, complexity, and coupling. They are impossible to eliminate. You cannot get rid of them, but you do have more control than you think. And with that, I thank you, and we'll return to the studio.